Well, hello everyone, and welcome from here in the energy corridor in Houston, Texas. It's a beautiful day in Houston right now. This is the best time of the year for us. So we appreciate you joining us today. Et bienvenue à tous. Nous avons une présentation aujourd'hui de Monsieur 𝗏𝗂𝗓 de Sonatrach. Ça sera un grand plaisir. So we do have today Mr. 𝗏𝗂𝗓 from Sonatrach. We're very much looking forward to his presentation on fractals and how they can be used in reservoir characterization. I always like to spend just a couple of minutes at the beginning giving a brief introduction to 𝗏𝗏𝗶𝗆, just in case we have some new audiences. And I think in general, we do have new people that arrive each time. So let me just give you the quick executive summary of 𝗏𝗏𝗶𝗆 for those of you who aren't familiar with it. So we meet regularly on Fridays, usually with the teams, to do global team meetings. But recently, since their work is done, we have what we call our Fearless Explorer Fridays. And so I'm going to give a special welcome, since we have Monsieur 𝗏𝗂𝗓 here today. We're going to give a special welcome to our team from 𝗏𝗶𝗱 this year, team 2015. They've been working very hard, and they're called the 𝗏𝗂𝗓𝗏 Mustang team. And of course, I welcome all the 𝗏𝗏𝗶𝗆 students who are in the Zoom room here. I see we have Mr. 𝗦𝗲𝗶𝗱, one of our lead mentors, and Professor Giorgio Minelli from Perugia University. So welcome to all of you. If you're not familiar with it, so 𝗏𝗏𝗶𝗆 is a 6-month part-time virtual internship for students. I'm not really aware of anything quite like this. It is collaborative. This is really key. It is global, as you can see from the pictures from some of our previous teams. And we're focused on the future. We're focused on what brings us together, the love of Mother Nature, the love of the subsurface, and we want to work together towards a positive future. We try and teach the skills necessary to be successful in the multidisciplinary, real-world, digital E&P setting. And that's what the wave of the future is. And the key here is that we have extensive mentoring from highly experienced industry experts like Mr. Forrest. These days, it's very hard to find industry experts within companies. And we teach many of the essential skills. The thing we like to emphasize most is the teaching of critical thinking. We use tools, we use technology, but those are just to help focus our critical thinking. So that's what we really try to teach, making excellent maps. You can't drill wells without excellent maps. And we teach the ability to draw. And we like to say, if you understand something, you should be able to draw it. Of course, this program was originally established between SEG and Halliburton. We have a lot of other companies sponsoring us, and that's key. So far, we have had more than 55 university teams, over 300 students from more than 40 countries around the world. By the way, we are about to launch the applications for 𝗏𝗏𝗶𝗆 Student 2021 within the next week or so. So in particular, if you're watching from one of these countries with gray, make sure you apply. We want to fill the whole globe here. And for those of you who are wondering, couldn't you do something like this and for people who are working, early career professionals? Yes, we call that 𝗏𝗏𝗶𝗆 Professional, and that's for individuals with 0 to 10 years of experience in oil and service companies. And thanks to Klaus Koster, your partner of Sonatrach, of course, chief geophysicist of 𝗏𝗏𝗶𝗆, we've been working with them to define the best way to do 𝗏𝗏𝗶𝗆 Professional. And by the way, we're going to be preparing shortly for 𝗏𝗏𝗶𝗆 Professional 2021 Session 1. So anyway, we have a lot of information on 𝗏𝗏𝗶𝗆. You can go to the Next Gen Training Partners website and the SEG 𝗏𝗏𝗶𝗆 Professional YouTube channel. So go to all these places. So now I'm going to introduce Monsieur Saïd 𝗏𝗂𝗓. C'est vraiment un grand plaisir d'avoir votre participation aujourd'hui. Je pense que vous avez une présentation qui sera très intéressante. So we welcome Mr. 𝗏𝗂𝗓, who's had a long and distinguished career at Sonatrach. He's currently head of the Geosciences department in 𝗏𝗏𝗶𝗆. So with that, à vous, Monsieur 𝗏𝗂𝗓, je vous présente et c'est à vous maintenant à manipuler votre ordinateur.
Donc, do you see my presentation?
Not yet. You have to press the green button. Yeah, not yet. It sometimes takes a few moments before it comes up.
And now?
Did you press the green, the share screen?
I didn't see the green.
It's at the bottom of your Zoom window. If you look at the bottom of your Zoom window, in the middle, there's a green button that says share screen. It's separate from the PowerPoint, of course.
Can we call Mario for?
You should be able to open your Zoom window where you can see all of us.
Yeah.
At the very bottom next to chat, there should be share screen.
So this is the window with Zoom, not the PowerPoint.
Where the arrow, green arrow?
C'est la fenêtre où on est tous présents. En fait, vous voyez toutes nos images. Alors en bas, il y a un petit truc vert qui vous dit share screen. Juste en bas, au milieu en bas. So if not, you have the slides, right?
Yeah.
Voilà, parfait. Very good. Well, thank you. Yeah.
Yeah, thank you.
And you can go full screen now on your PowerPoint.
Yeah. Yeah. Is it good? Can I begin?
Voilà, parfait. Please go ahead. Very good.
Yeah, thank you. Ladies and gentlemen, good morning, good afternoon. First of all, I express my sincere thanks to 𝗬𝗶𝗱 to be here and to give my lecture on the stochastic fractal model, which is specifically the multifractional Brownian motion, in short, MBM. I extend my special thanks to all the participants who joined us. In fact, there is now a significant number of papers and researchers dealing with the application of MBM in geosciences, and one purpose of this presentation is to review some applications of this model on geosciences datasets and thus demonstrate the contribution of this model in our field. More importantly, we think that it's of interest to lead a wider audience of researchers and students to be aware of the potential benefits of this process to foster new applications. For illustration, I present this image, which presents geological branching fractals, which are fractal patterns found in nature. Regarding the outlines which will be discussed during this presentation, firstly, in introduction, I briefly introduce the evolution of fractal models. Then I give some important insights into fractals, fractal theories such as Euclidean geometry and its limitation, fractal geometry and fractal objects, some fractal properties, and also I introduce the stochastic fractal processes, which are fractional Brownian motion, in short, FBM, and the multifractional Brownian motion, in short, MBM. Thirdly, I present a review of the different applications of this process in geosciences using well-logs data, airborne spectrometric gamma ray, core image, geomagnetic time series, sea level variation data, and terrain or topographic modeling. Ultimately, I will conclude with some thoughts about MBM model. Extracting useful information from observation requires advanced processing and interpretation techniques. In this view, fractal theory is suggested with regards to successful applications in all aspects of geosciences fields. Mandelbrot and Vanis have proposed a statistical fractal model called fractional Brownian motions, which has been used to characterize several types of signals in geosciences. The most widely set of models is based on fractional Brownian motion and its extensions. This model has been used for mountain synthesis as well in the fine description of the C4 floor. One of the reasons for the success of this model is that it shares an important property of many natural signals. That is, statistically, a natural signal is the same at several resolutions. FBM allows to model the scale invariance property as well as to control the general appearance of the signal via a parameter h taking values from 0 to 1. When h is close to 0, that corresponds to an irregular signal, while h around the value of 1, we have a regular signal. A major drawback of this model of FBM is that its regularity or smoothness degree is the same at every point. This does not fit into reality, since real signals present time-space varying regularity, so it is suggested a more generalized model, which is the multifractional Brownian motion, in short, MBM. This model goes beyond FBM by allowing h to vary in time and space. It is obtained by replacing the real parameter h of FBM with a continuous function h whose values ranging between 0 and 1. With this slide, I would like to show that all man-made objects are made up of Euclidean shapes as triangles, spheres, prism, etc. But what about these familiar things with different scales from the natural world? A leaf, a tree, a lightning, mountains, and finally, an Earth view as seen from space. Can they be easily described with Euclidean shapes? To answer to this question, I would like to mention that while we haven't yet defined it with what is a fractal is, here are some fractal representations of some of the things that Mandelbrot said that clouds not easily represented with traditional geometry. This looks a lot more like a cloud than this does. And this tree looks like a tree than this does. So the secondary highway cannot well describe the tree. Benoît Mandelbrot, the founding father of fractal geometry, said that clouds are not spheres, and mountains are not cones, coastlines are not circle, and the bark is not smooth. Nor does lightning travel in a straight line. In fact, fractals are geometric figures, just like rectangles, circles, squares. But fractals have special properties that those figures don't have. They are mathematical hedras that replicate themselves by fragmentation. The term fractal is coined by Mandelbrot in 1975 and was derived from the Latin fractus, meaning broken or fractured. Using this geometry, complex pattern of nature like coastlines, clouds, and mountains can be mapped. A fractal is a geometric figure that can be broken down into parts. Each part is a reduced size copy of the whole. The fractal uses the idea of self-similarity to make its design. Self-similarity means that as you magnify, you see the object over and over again in its parts. Fractals are complex, infinitely complex, and chaotic. With regard to its fractional dimension, it's an integer dimension, not as in the case of Euclidean objects where we have 1 for line, 2 for a plane, 3 for a cube. Amazingly, these beautiful objects of breathtaking complexity are generated by relatively simple mathematical processes. In mathematics, self-similar objects exactly or are approximately similar to a part of itself. So this part is similar to this part, and so on. So the whole has the same shape as one or more of the parts. Many objects in the real world, such as coastlines, are statistically self-similar. So parts of them show the same statistical properties at many scales. In fact, self-similarity is a typical property of fractals. Scale invariance is an exact form of self-similarity where at any magnification, there is a smaller piece of the object that is similar to the whole. For instance, I present the side of the 𝗏𝗏𝗀𝗁 snowflake, which is a figure, a geometrical figure, which is symmetrical and scale invariant. The fractional Brownian motion is the well-known and popular stochastic fractal model. It is parameterized by the Hurst index, which measures its self-similarity and quantifies the strength of time correlations. It is defined as a continuous zero-mean Gaussian process null at the origin and displaying stationary and self-similar increments given and defined by its covariance function. The increment process is known as fractional Gaussian noise. FBM processes were found to be self-similar over a wide range of the length scales. These relations means equality for all finite dimensional distribution. This means that the simple part of both sides of this equation cannot be statistically distinguished from each other. H is called self-similarity or Hurst parameter that implies that a affine dilated subset of one simple part cannot be distinguished from its whole. It is therefore not possible to identify a reference scale of time, and thus there is no such reference scale. Indeed, the Hurst exponent H describes FBM behavior in terms of spatial correlations and long-range dependence properties. It is used to know whether the process Brownian motion, in case H equals 0.5 or half, or persistent when H is between a half and 1, and anti-persistent when H is between 0 and a half. A persistent process doesn't unexpected rapid change, what we call long memory. That means that deviation tend to keep the same size. There is a good or strong correlation between samples. While in the case of anti-persistent FBM, there is no spatial, there is no correlation rather, we have anti-correlation of samples. So deviation of one side are generally followed by deviation with the opposite side. Also, H specify the fractal dimension of the fractional Brownian motion. It measures the strength of the regularity or the roughness of the FBM surface topography. The fractal dimension is calculated using this relation. When H is close to 1, the sample is weakly irregular, while for H close to 0, it is highly irregular. In the frequency domain, FBM are governed by scaling law. That means that the power spectral density is proportional to the frequency of the power of minus beta. That means that it decays algebraically as frequency increases. The scaling law can be revealed by the log-log plot of the power spectrum, which is characterized by linear shape of slow minus beta depending on the Hurst exponent value. Beta, the value beta is determined by linear fitting of power in log-log plan, and its value vary between 1 and 3. To measure the strength regularity of a stochastic process at the type T, the pointwise exponent alpha is calculated. Mathematically speaking, alpha represents the differentiability degree of the signal. For all the realization of an MBM, it was demonstrated that the regularity, the exponent, the pointwise Hölder exponent equals Hurst parameter for almost realization of FBM process. Therefore, alpha or H specify the strength of the regularity or roughness of FBM profiles of time series. The larger alpha exponent, alpha or H exponent, since they are equals, the more regular and the more and smoother signal we have. When we increase the value of H, the signal becomes more smoother. Since FBM model has everywhere the same local regularity H, it doesn't allow to analyze signals having a regularity which varies in time or space, as are most signals in geosciences. So multifractional Brownian motion it's a model that was introduced as a generalization of FBM to overcome this limitation. It was obtained by replacing H by a continuous function H versus time. But no longer stationary nor self-similar, MBM offers the advantage to be very flexible since it can model phenomena of a simple path display of time-space dependent regularity. Like FBM, for all realization of an MBM, it was shown that the regularity pointwise Hölder exponent alpha evolves over time, and its value at each time t, it equals to the Hurst parameter at the same time. For recall, H value varies between 0 and 1. Thanks to its versatility, MBM has gained acceptance in many research areas. I would like to show that we can see Brownian motion that corresponds to process with H equals half is a subset of FBM category, which is in turn the subset of MBM. We have to keep in mind that an MBM is a combination of FBM paths. It means that each time T, the FBM is regarded as an FBM with a Hurst index time. So the MBM can be regarded as a combination of different FBM paths. Here I present some simulated MBM path with different regularity functions: linear, periodic, logistic, and synthetic. The first column represents the constant regularity function, while the second column shows the corresponding simulated path. For all the used types of regularity function, the ambient paths are becoming smoother as regularity function take a higher H values. The higher H values, the smoother are the paths. They are smoother. The equations FBM and MBM defined earlier for one dimension are extended to the second dimension. Therefore, the resulting FBM and FBM paths, as well as the harder functions, will be surfaces instead of simple one-dimension functions. In addition, here we consider Euclidean norms instead of absolute value for the one-dimensional case. Similarly to the monodimensional case, or the relation of an MBM, the regularity pointwise alpha depends on the position xy, and its value equals to the Hurst parameter at this position. For illustration, two-dimensional FBM paths are simulated using different value of Hurst value, varying from 0.1 up to 0.9. The H value controls its roughness or its regularity, and as H increases, the FBM surfaces become smoother. Here, the two-dimension MBM paths have been shaped using harder functions with different types. Bilinear for the first line, logistic for the second one, and the periodic function for the third type. That illustrates that the variable regularity property of MBM with trajectory obtained with different H functions. The versatility of MBM makes this model appropriate to deal with numerous real phenomena at the expense of more mathematical complexity. To demonstrate the potential of MBM and to highlight the benefits of this process in geosciences, I will review the main applications of this process in the following topics: well-log data, airborne gamma-ray spectrometric data, digitalized core image, geomagnetic time series, study of variation in sea level, and finally, terrain or topographic modeling. For each topic, only the main findings are presented. Of course, references will be given in each application to let attendees to get more details on the shown applications. Our first application of multifractional Brownian motion process deals with well-logs data. Previous research showed that the fractal behavior of well-logs and suggested fractional Brownian motions FBM to model them. This study investigates the multifractional property of velocity logs data recorded at two scientific borehole, the 𝗙𝗏𝗶𝗱 borehole and the main 𝗙𝗏 borehole, derived for the German continental deep drilling program 𝗙𝗏. In this study, we try to establish a relationship between regularity profiles and ethology, and show that the Hurst function may then constitute a tool to characterize underground heterogeneity. The first regularity profiles are computed from P wave velocity and S wave velocity log. So we have the regularity related to VP, and this one related to VS log. Then using a geological sketch of crossing the well log, crossing the 𝗙𝗏 wells, or lithological sketch of the study area, we establish a correlation between the regularity profiles and the lithology encountered of the strata. In other words, we carry out a lithological segmentation on the estimated Hurst curves, and where we identify the lithological discontinuities such as layer boundaries or faults compact. The variety of the resultant H values with depth allows us to detect the topological units crossed by the wells. And the recognized topology are 𝗦𝗶𝗶𝗆, gneiss, and variegated. Also, we have identified 6 faults crossing the well: F1, F2, F6. Another important finding is that regularity profiles are strongly correlated with porosity. Comparison of KTB estimated porosity logs and the regularity profiles. The regularity profiles and porosity logs. This comparison demonstrates a significant relation between the local extrema of H value exponent function and the fluidical fractures. It is established that the local extrema values of the regularity profiles corresponds to fractures zones characterized by high values of porosity. These high values of porosity correspond to the fracture zones. Another application is performed on Algerian exploration with log data. The investigation of the results obtained from different datasets reveal a clear correlation of topology with some regularity profiles, mainly those derived from VP, VS, and MK logs, which measure the liquid field porosity. However, the regularity profiles derived from the other logs don't allow to recognize the different geological discontinuities on all the datasets. This may be explained by the weak dependence of these logs on the porosity. These findings are in agreement with the results of our previous work on KTB velocity logs. Worth mentioning results yielded by a strong correlation. A strong correlation between the estimated regularity profile from different wells. Almost the regularity profiles related to each well, except for well logs, well 4. All the regularity profiles are strongly correlated. You can see the high value of correlation coefficient value, except for the 4th well, where we find some weak values between gamma ray regularity from gamma ray logs and regularity related to resistivity logs. The third application deals with P and S wave velocity taken from Algerian wells. It is shown that regularity analysis allows to extract meaningful information regarding the nature of the fluid present in the investigated geological formations. The discrepancy between the regularity profile obtained from VP and VS is due to the presence of water, as is the case of first well, well 1, and the second well. While we noticed the presence of gas for the third well, presence of water here, always in the same in the third well, and also presence of gas here for the fourth well. Here we try to establish a possible relation between the change of order exponent H value and the physical parameter velocity. We try to plot scatter diagrams. Each depth is represented by its coordinate velocity and its exponent H exponent value. The color indicate the point's density. All these scatters show an irregular distribution. So they can be described by deterministic function. And the red circles mention points with high density on the scatter diagram. And we can conclude that these values varying between 0.1 and 0.3 generally they correspond or they confirm the anti-persistent nature of the investigated velocity logs BP and VS. And also highly heterogeneous geological formation corresponds to a very fluctuating seismic velocity and path to a very weak H value. Another study illustrates the clear relation between regularity profiles derived from BP and VS as shown by this table. This means that the regularity is a robust property of lithology and can thus be used as an additional input for neural network models to estimate VS from VP. Here we present the application of Hölderlin regularity to estimate VS from VP using multi-layer perceptron artificial neural network. In addition to VP, which is the first input, we consider the regularity log as the second input of the neural network model. Besides, the suggest model used empirical mode decomposition to decompose VP log data into a set of intrinsic modes functions. These modes are used to construct a high frequency component or low frequency component, and finally a trend component using Hölderlin regularity-based find-to-source reconstruction algorithm. The suggested neural networks-based prediction corresponding to the least mean square error is more reliable than the other techniques discussed here in the study. Therefore, this technique is a powerful tool for prediction S wave velocity from VP. Okay, the second application of MBM is on airborne spectrometric data. We try to show the fractal behavior of the analyzed gamma ray measurement, and we try to show the multifractionality behavior of this data by showing the variation of each exponent value, variation of this each value versus depth versus position. In addition, it is demonstrated that this behavior is not, fractal behavior is not affected by all the pre-processing operations, spectrometric correction and interpolations. So we can conclude that these corrections are not then requested. So for analysis purpose, 5 vertical profiles from measurement in uranium channel extract from data. On the left, the measurement profile. In the middle of the module of the amplitude spectrum of the measurement profile versus the wave number and log scale. And on the right, we represent the local Hölder function. And the blue represents raw data. The red corresponds to corrected data, and the green is related to correct and interpolated data at the same time. So as we can see, all the calculated amplitude spectra decay algebraically. So the analyzed data present a fractal behavior. Moreover, the analyzed data present a whole exponent value varying with the latitude of the measure. Hence, the data can be considered as multifractional Brownian motion processes. A significant result deserves to be noted is the fact that the spectra obtained from all of the three types of measurement, raw data, corrected data, and corrected and interpolated data, display a similar form. So the applied cooperation, I mean corrections and interpolation do not affect the fractal aspect of the raw data. Consequently, the spectrometric corrections are not requested for a fractal analysis, which can be carried out directly on the raw measurements. By doing so, the stochastic component of the measurement is kept unaltered or intact. Here to mention that all the regularity maps derived from the measurement of all channels exhibit almost an identical form. This is why only the local regularity map established from your uranium channel is presented. By reporting the fault affecting the studied region on the obtained regularity map, we remark that the fault locations correspond to local minima H value, and the main accident for the 15 minutes fault is perceptible on almost all the regularity maps. However, the regularity maps present local minima H value in some locations, probably due to less important faults which will be checked further on updated geological maps. Now we try to establish a correspondence between the obtained regularity maps and the geological map of the area. On the considered geological map, we delimit in dotted lines the geological formation. The same color corresponds to the same geological facies. It is shown that the considered geology, lithology don't exhibit the same H value. These obtained preliminary results reveals that the H value cannot be used as an attribute to characterize lithology, while it could be used for the recognition and the establishment of the network faults. Regarding the third application, here we suggest to go beyond the conventional core analysis by applying a new fractal-based approach to extract the maximum features from a core image. The basic idea behind this work is to perform a local regularity analysis on digitalized core image data. The investigated core is extracted from a well drilled in an Algerian basin. The selected core highlights the main geological features of the region under study. The core presents sandstone, clay, and quartz cemented cross-stratification underlined by mud films. The formation is affected by the main fracture F1 and another less important fracture F2 sub-parallel to F1. The processing of the core image requires first its digitalization. The core image is digitalized and codified in gray levels with integer values ranged between 0 and 255. First, the fractal behavior of the digitalized core image data is investigated on 5 horizontal and 5 vertical profiles as illustrated. And here we present an investigation of the fractal properties of the 5 vertical profiles extracted from the digitalized core image. The left column represents the profile of digitalized core image data. The middle, it's the amplitude spectrum module of data with respect to the wave number and log scale. And finally, the right column represents the variation of the local H exponent versus the position. As can be noted, all the resulting amplitude spectra exhibit an algebraic decay that confirms that the fractal properties of the digitalized data. In addition, the analyzed profiles present a varying regularity with the position y. This can be assumed or described as ambient paths. In fact, the variation of each exponent is originated from the local topological change of the composition. Just to underline that the same results have been obtained from the investigation of horizontal profile extracted from the digitalized core image. From this figure, it can be seen that the analyzed data present a varying regularity in the XY plane. It is again confirmed that the digitalized core image can be modeled as a 2D MBM, and the obtained H maps highlights where the main fault F1, the break, and the mud films. However, the minor fault is locally noticeable. As mentioned in the previous applications, these topological changes are marked by local maxima of each values which are higher than those characterizing the surrounding medium. Now we present an application of ambient process to geomagnetic activity. A geomagnetic storm can be referred to as a solar storm, is a temporary disturbance of the Earth magnetosphere caused by a solar wind shock wave and or cloud of magnetic field that interacts with the Earth's magnetic field. A geomagnetic storm has three phases: initial phase, the main phase, and the recovery phase. Near the approach of storm onset, the scaling exponent settles down on fluctuates near a value of 0.5, the indicative of Brownian motion. Around the time of onset, commencement of storm, the main phase, this exponent rapidly jumps to 0.7 and stay approximately constant for several days. This rapid jumps, as shown by the dotted vertical line, is an indication of modes transition, and this jump corresponds to the approximate time of space storm main phase. The secondary research deals with geomagnetic fields component and the corresponding local Earth exponent H. For both geomagnetic time series, we notice that the average value of local Earth exponent is always higher than 0.5, suggesting that the mean character of geomagnetic time series is well in agreement with that of a persistent MBA. The fourth application dealing with the study of the sea level variation. Here we will exhibit that there is a multi-scale property of sea level based on the study of regularity of sea level. Data recorded at 6 stations in Florida and Eastern Gulf of Mexico. This work, the contribution of this application are twofold. Firstly, the older exponent of sea level may not change with time constantly at time scale, small time scale, for example, daily time scale, but it varies significantly at large time scales, such as monthly time scale. Secondly, the second contribution is that the dispersion of the older exponent of sea level may be different from a station to another. This implies that the older roughness of sea level may be spatial dependent, as we can see for both. Daily series of sea level, the older exponent varies with time very slightly. January 1 and January 2. However, the weekly series of sea level at this station are associated with Hölder exponent monotonically increasing for the first week, decreasing for the first week and increasing for the second week. So the Hölder exponent of sea level at the weekly time scale may not vary considerably enough. On the other hand, the Hölder exponent of sea level at the monthly time scale vary with time significantly. Now we investigate the Hölder exponent of sea level R at large time scale. We notice a significant variation of each exponent at large time scale. In addition to the variation of Hölder exponent over large time scale, the variances of the Hölder exponent of sea level at different observation stations may be considerably different, as shown by discrepancy of variance value. So we are from 10 minus 4 to the power of minus 4 till 1.17. 10 to the power minus 3. This motivates us to suggest a spatial time modeling of the Hölder regularity of sea level. The last and the least, and not the least, application deals with the topographic modeling. In most places, the surface of the Earth is rough and rapidly varying. So, two-day dimension random processes are often used as models for digital elevation modeling. In addition, most topographies display a form of an approximate self-similarity. That means the same features are statistically observed at various resolutions. For these reasons, fractal stochastic processes are popular models for digital representation of ground surface topography. In this regard, research has shown that zones of high altitude are rougher than regions of lower altitudes. The self-regulating multifractional process, in short, SRMP, is an extension of MBM model. The motivation for introducing this model is based on the following general fact that in nature, the local regularity of phenomenon is often related to its amplitude. So the plain area with low altitude are automatically smoother than mountains area with high altitude. So a self-regulating process is defined as a stochastic process such that almost surely at each point the Hölder exponent is a deterministic function of the amplitude. In other words, almost surely at every point x alpha is a function of its altitude zx, where g is a deterministic function characterizing the process. For illustration, we present the realization of two-dimensional self-regularity multifractional process with its associated regularity map, as well as the scatter diagram showing the density of points in the exponent altitude plan. Here, the used deterministic function g is linear, gz equals 1 minus z. To conclude today's presentation, I would say that, as discussed previously, MBM offers the advantage to be very flexible, since it can model phenomena whose sample path display a time-space dependent regularity. The strength of this process, fractal process, in the analysis of stochastic data has been demonstrated through the presented applications on wavelength data, airborne spectrometric gamma ray data, core image, geomagnetic time series, variation of sea level, and finally digital elevation or topographic modeling. To model in a more satisfying way natural phenomena, as the case of ground modeling, self-regulating multifractional process, which is a generalization of MBM, has been introduced. In contrast with MBM, SRMP takes into account the relation between the amplitude of the signal and its Höllderian regularity. This special feature of SRMP makes it very practical to model real data, and we expect that it will gain an increasing interest in various field research areas. Thank you for your time and interest. I will be available to answer any of your questions. Thank you.
Okay, well, thank you very much, Monsieur 𝗏𝗍𝗂. Très bien, it's good. You have the references there. I was hoping you would have those. That way, if anybody wants to follow up on some of your papers there, they'll be able to do that. Yeah, maybe leave your contact information there for just 1 second while we're filming, you know, so to speak, so everybody can write this down in case they have any specific questions they want to send to you.
Yeah.
So I think we can now maybe unshare your screen, which is the stop. I think is it at the top? It should be at the top, a red button. Should say stop share. Yeah, there we go. Perfect. Okay, well, thank you very much. So we're going to give you a digital round of applause here on behalf of everybody.
Thank you.
There we go. Yeah, the modern world. So anyway, thank you very much. Very interesting. You've done a lot of work in this area for many years. It's clear. So very, very interesting. So we're going to invite anybody now, whether from the students themselves in the Zoom room, who can ask you questions directly because you can see them and they can see you. If any of you are on YouTube, you can submit your questions via chat. Those will be forwarded to us. And since we may have a multinational audience, those of you who want to submit your questions in French, no problem. We'll be looking at them in the chat and translate. So let's just see quickly. First of all, maybe the students. Do we have any of the evolved students that had some specific questions they wanted to ask Monsieur 𝗏𝗍𝗂 here today? Okay, that's fine. And we're going to be collecting the questions on the YouTube. I guess one question I personally had is just to understand, I mean, you showed many different applications, right, in which you take a well log, you take maps, and then you calculate the fractal parameters, the H exponent, etc. How do you do that in a practical sense? So are you doing much of your work, it looked like maybe in MATLAB, or you have some other tools that you do the analysis or the calculations in?
Yeah, in fact, there are different algorithms to computations. I didn't insert them in this presentation. I think that it will be very boring with mathematical formula. So I developed my codes on MATLAB. Different methods for simulating and FBM and MBM maths be in 1 dimension, 2 dimension. And also I developed some codes, MATLAB codes for regularity estimation for both cases, 1 dimension and 2 dimension.
Okay, so you have different codes then for when it's like a well log, a series of versus the 2-dimensional case.
Yeah.
Okay, and what about 3 dimensions? Not yet, or?
Not yet, since I haven't data. I haven't 3-dimension data, so I didn't.
Well, I mean, obviously, it would be interesting at some point to move into third dimension with things like seismic volumes. But you know, we can arrange to get you some data sets, by the way, if you're interested. And three
Thank you.
dimension.
Thank you. Just I would like to just to point out just a point that we can consider MBM process. We have first to check fractal properties of the data. Then we can extend the data, the analysis, by considering MBM analysis. I think I tried to do this with the seismic data. Unfortunately, the data, seismic data are not fractals. In contrast with the MBM, we have logs data. Logs data are fractal. Display fractal behavior. In contrast with seismic data, they aren't, so we cannot consider them that they are fractal models, fractal data.
So in the end, what do you think it means in terms of geology if something is fractal or if it's not fractal? I mean, you said seismic is not fractal, but logs are fractal. So is that something about a repetitive process in Mother Nature, or what does it tell us if something is or is not fractal?
Mathematically, we can check this property through correlation, cross correlation or autocorrelation function, but practically we use more power spectrum data. So the condition we have to in the frequency domain we have the power density should be display in algebraic decay.
Okay. But does it tell us something about the process in Mother Nature, like cyclical deposition? Is that why the logs are fractal, or what does it really tell us?
Fractal, practically, that means heterogeneity degree when it's homogeneous. So it's more regular, it's smoother. Contrary, when it is heterogeneous, so we have irregular signal, rough signal, with fluctuations, and it's physical explanation of fractality. And this may be related to phenomena physical like in well logs that corresponds to the geometry of each value corresponds to lithological discontinuities like layer boundaries or fault contacts. In core image, practically the same thing. In geomagnetic time series, that the variation of each value corresponds to the beginning of the main phase of the star. So in each discipline or in each field, the meaning may be a little bit different but in general, that corresponds to the heterogeneity of the process.
Okay.
Yeah.
Okay, let's see if any of the other students, of course, these students are all very smart. They can derive the wave equation, the geophysical wave equation in their sleep, you know, from first principles. So they're they understood all the equations there, which, you know, I'm not as smart as they are, but do any of our very clever students have any questions themselves? Or is this, maybe I should ask Professor Minelli, is this being taught widely in some of the universities in Italy, or you have to unmute yourself, by the way. Oh, no, I think we need the volume louder. You're still, yeah, your
Hello.
volume. Now we can hear you, yeah. So yes, is this being taught in the universities in Italy, or?
Yes, I have one of my colleagues, he is a petrographer, and he uses these techniques for classification of volcanic rocks.
Yeah.
And also with study of grain size distribution in pyroclastic.
Yeah.
And he did many of his talks about, but I really have difficult to understand, to link the reality with the numbers. And
Yeah.
I am like you, Alan. I got a big problem with
Well,
this big mathematical brain.
well, I think you know really.
I
I was going to just make the general comment.
I just want.
I mean, I was just going to make the general comment that, you know, any field doesn't matter. You know, there is a phase, there are the equations, and then there's the underlying numbers, and it doesn't matter. It could be acoustic impedance, or it could be VS or some other attributes. And then it takes time to build the experience and to absorb what that means in terms of the geological factors and so on. But yeah, I tend to draw the empirical conclusions or the visual conclusions. Usually I liked your chart where you're showing the density of, for example, with the color bar and the density, which I think was a MATLAB display, and the VP and the VS and where those points were falling. So I thought that was quite interesting.
Many years ago, I got a colleague in ENI. Now he left ENI. I think he's in Oman and some place like that. And he works with fractal distribution in the reservoir modeling about fractures distribution. And according to his idea, his chart, he got very good results, but were always something confidential. They have he was able to get into the dynamic modeling of a reservoir, the geometry in the the distribution.
We have just
he got very good result.
We have just
but I don't know much more. Sorry.
We have just published a paper. It was accepted yesterday.
Oh.
But deals with just yesterday. Yeah.
Wow.
But deals with discrimination between using WebLogs. We can discriminate between nature of fluid. So oil, if we have oil reservoir or gas reservoir, just using the multifrac, another concept, but practically it's related to this. But just using this the fractal dimension or fractal exponent, we can discriminate the reservoir depending on the fluid, oil or gas or water. The work has been performed on maybe roughly 100 well logs. So it's very statistically it is very reliable to announce this statement.
Yeah, it sounds like Sonotrack and ENI are the leading companies using this. Let's see. I see we have Mr. Jonathan Torres here. Did you have a question? Let me introduce him. So I think you all know Jesus and Mario that work with me. I also currently have two other interns working with me. So one is Jonathan Torres, and the other one is Rob Thompson here. And so now that they're interns, they get the same abuse as Jesus and Mario. So over to you, Jonathan.
Yeah, I was just gonna ask if you use this technique to model river meanders, and if so, how do they compare to other models and what we see in nature?
So the meanders of rivers.
Mm-hmm.
I didn't do this application on rivers, not yet. No.
Okay.
I did it for geophysical signals data. Yeah.
Okay.
Yeah.
I think there are some paper about the meanders distribution, the meanders shape versus lithology. with study with this kind of techniques. I think
Yeah.
there is. I think to remember something like.
Yeah.
So the geomorphology and the lithology, you're
Yes,
saying?
geomorphology is one of best place to work with this kind of techniques.
Okay.
And it will be beautiful to get a kind of 3D analysis, as Alan said. But it's only there is always the same problem. It's difficult to get data set. but you know, I never try. Sorry, but
Yeah, you can try.
I think to remember there is something in bibliography. I can look for it and send you some reference.
Okay. Okay. Very good. Okay, let's see. And do we have any other questions? I guess anything either coming through the chat or anybody else?
Yeah, since I came a little bit late due to work, I wanted to ask if the presentation will be published because I would like to recheck the references again.
Yeah.
If this would be possible.
So all these presentations from our Fearless Explorer Fridays are on the YouTube channel. So you would just be able to, that is why I.
Okay, because I just checked the link and it wasn't working for me right now.
Yeah, but that's we're still live. We're still live.
Okay.
Yeah. So usually it takes, I forget, Mario could tell us, but it takes a few hours. So really you have to wait kind of a day before you can go to the link. And that's why I asked Mr. 𝗏𝗂𝗧 just to stop so that when you're in the video, you can pause it at the right spot and get those references. And you've obviously published, you must have a long publications list, Mr. 𝗏𝗏𝗧.
Yeah, I can give you all the references. I have it. I have all of them at the end of the presentation.
Yeah, this would be great. Universities also not in this field, but we're also working with fractal dimensions. We are trying to link the displacement patterns with the Lemma diagram and fractal dimensions. So maybe this could also give me a little bit of additional input.
Yeah.
Also, I see we have another question here in the chat. So this is a question that is, you showed us, I think, the core image. You had the image of the core with the fracture. So someone asked about the borehole image itself, in the borehole image viewer. So could you use this approach in the actual borehole image itself when you have 2D images from the borehole to improve your understanding of the geological features in there?
You mean that if I can apply this approach on this data?
Yeah, but I think it means on the image. You know how when they have the borehole viewer, they basically unwrap the picture and then you have a 2D image of the borehole. So the question is, could we use these same techniques on the 2D image from the borehole viewer tool?
Yeah, I think that we can do it. Yeah, we can do it. We have to implement the method and we check the results.
Yeah. I mean, if you could do the core image, it seems like there's no reason why you could use the borehole televiewer image at the same, same way.
It will be processed as an image, so we can process it with the same manner.
Okay. Well, I think there are no more questions. Thank you from the participants here in the room. Some of the people. Yes.
There's
go
a
ahead.
question in the chat from YouTube.
But I think that's the one we just asked, unless there's a new one. That was the borehole image one. Yeah, I saw that come through.
Perfect. Okay, then yes.
I think that's it. And I think we'll close out. I'll show a few quick slides to close out. But again, merci beaucoup, Monsieur 𝗏𝗂𝗧. C'était un grand plaisir d'avoir votre présentation aujourd'hui. Et donc, je crois que vous avez trouvé pas mal d'intérêt. And you'll all be reading Mr. 𝗏𝗏𝗧's papers, and when you students all understand the equations, come explain them to me, because that's above my level. So anyway, let me share. We usually close out. So again, let's have a round of applause for Monsieur 𝗏𝗍. Thank you very much for the presentation. Yeah.
Thank you.
And
Merci.
stay in touch.
Merci à vous.
Yeah, Professor Minelli. Yeah. So I'll close out and then we'll come back because, you know, some people are going to go to other meetings. So I'll do like a little closeout as I always do. And let's just quickly kind of talk about what's coming up, by the way. So for the students, pay attention. Okay. So looking ahead now, we have actually quite a few upcoming events here. So first of all, next Friday, we have a talk from an ex-shell geologist that Mr. Forrest worked with, Dr. 𝗏𝗏𝗀𝗆𝗁𝗏. And he's got a very interesting paper on bright spots and AVO in the Niger Delta. And maybe we need to see if we can get some of that data to Mr. 𝗏𝗏𝗀 here to try some 3D fractals. We're working on a talk on Python applications in 𝗏, probably the following week. And of course, we'll send official invitations to that. We're coming up to the AAPG annual meeting next week. And those of you who are interested, I'm part of a panel discussion talking about the skill sets needed in the future. And it'll include Dr. Sharon Mosher. She's the former dean of University of Texas at Austin. And, you know, we get many questions these days about carbon capture and storage and other applications of our skills. So anyway, that's those of you who are attending the AAPG meeting. I'll also be talking at the UPitch session. And then, of course, everybody put in your calendars the SEG annual meeting. Those of you who are going, the students themselves will be presenting their Evolve Best Investment Opportunities within the SEG annual meeting on October 12th. And then on Friday, October 16th, 9 o'clock, we will have the 2020 teams recognition and celebration. So I hope all the teams will be present for that. So quite a few upcoming events. We will actually be unveiling our Project X video. The students know what Project X is, our Happy Evolve 2021. So you all owe us some videos of yourselves. So make sure you send us your videos for Project X. And if any of you are watching and you want to support Evolve in some way, either by sponsoring teams, you know, there are costs associated with running Evolve, or if you wish to make small contributions to SEG as low as $10, we'd welcome you doing that. And so really to close out, you know, it's been a tough year in general, but Evolve 2020 has just been a very successful year. We have kept going. And so on behalf of the students, SEG Evolve, we are not afraid of the future. We are the future. And so hopefully we will see you next time at one of our Evolve events. So thank you to everyone.
Thank you.